The divine proportion in this flower is living proof of our holy design.
Wow, I don't think so.
The divine proportion, often known as the golden ratio, has confounded humankind for millennia with its supposed mystical powers. It is seen by many to open the door to a deeper understanding of beauty and spirituality, and others dismiss it as coincidence or entirely untrue. The ratio is approximately 1.618, and it is suspected to have been first stumbled upon by Pythagoras. He and his followers adapted the pentagram as their symbol, as it represented health and, more interestingly, what is now known as the golden ratio. In the pentagram, a 5-pointed star, he found that the ratio of the length of a segment to the next smaller section was a mysterious and incommensurable number that cannot be expressed as a ratio of whole numbers. Similarly, in a pentagon, a 5-sided polygon, the ratio of the diameter to its side is also the same number. This astounded the Pythagoreans, as their worldview was based on the intrinsic properties of whole numbers. The realization that there exist numbers that go on forever without displaying any repetition or pattern caused a philosophical crisis. Many centuries later, Leonardo Bigelow, an Italian born in 1170, discovered the unusual properties of a numerical series that bears his nickname, the Fibonacci sequence. While studying how fast rabbits could breathe, he came up with a logarithmic sequence whereby each number is derived by adding the previous two numbers. For example, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and so on. And if we arrange squares whose widths are equal to the Fibonacci numbers just so, we get a spiral that is often observed in nature. The ratio between any two successful Fibonacci numbers is very close to and approaches 1.618 as the numbers increase. The term golden ratio was actually coined during the mid-19th century, and it wasn't until the 1900s that the Greek letter phi was used to designate this proportion. More recently, the golden ratio has seen another resurgence in popularity due to its being featured in Dan Brown's immensely popular and controversial novel, The Da Vinci Code. In it, Brown makes several claims regarding the golden ratio, including that it can be found in the human body and in all sorts of art and architecture. Throughout the 20th centuries, many studies were conducted to analyze psychological preference for the golden ratio in aesthetics, but the overall results were inconclusive. Researchers often succumb to predetermined bias towards confirming it or disproving it. Additionally, perspective always comes into play whenever mapping a three-dimensional object onto a two-dimensional shape. So, does this mean that it's all bogus? Not so fast. The fact is that the golden ratio does have some interesting mathematical properties, and it does occasionally appear in nature. So rather than simply accepting it as divine or blindly dismissing it outright, let us explore the nature of the golden ratio. On many plants, the number of petals is a Fibonacci number, like lilies with 3 petals per row and pinks with 5. And the arrangement of seeds on a flower head also follows a similar pattern, as well as pine cones. And the patterns can be found in the arrangement of leaves as well. Why do plants grow to maintain this design? The reason seems to be that this arrangement forms an optimal packing. Plants grow to form a single group of cells at the tip of each twig called a meristem. Once formed, they grow in a spiral fashion, turning the stem by an angle as the new cell appears. These cells may then become a new branch, a petal, or a stamen. But how do plants determine the optimal angle? Through millions of years of trial and error. Let us examine this process on our own model flower. First, we see that if it did not turn at all, the new seeds would push out the older ones in a straight line. If, however, they rotate half a turn, each new turn will push 180 degrees, alternating around a circle and resulting in 2 straight rows. If they rotate a third, then it takes 3 rotations to complete a turn, and they get 3 rows. And if they rotate 2/3, it just takes every other third, but ultimately settles down on 3 rows again. So it seems that the denominator determines the number of rows. Let's make sure. 1/10 results in 10 rows. 2/10 results in, hey wait, 5 rows? Oh, this flower is really good at math. It knows 2/10 is the same as 1/5. Okay, let's increase it a little bit from 1/5 and see what happens. The rows are beginning to curve and form a stronger structure, but still not an ideal spread. In fact, any number that can be written as an exact ratio, a rational number, is not going to give us a good result. What we need is an irrational number that never settles down to a rational approximation. Let's try to figure out the simplest number that qualifies. We're going to multiply the angle of the last seed by 1 plus a little bit. And the little bit has to be less than 1 to avoid going full circle, so we'll have to do 1 over something, and keep the denominator more than 1 to keep it small. But that something cannot be a whole number because, as we've seen, the denominator causes straight rows. So let's do 1 over another something. And we want an irrational number, so we should repeat the process on and on. We get 1 plus 1 over 1 plus 1 over 1 plus, and so on. And if we do the math, this formula collapses to 1.618. Does that number look familiar? We just arrived at the golden ratio. Let's try our number on the flower. Pretty good distribution, wouldn't you say? So, as it turns out, the golden ratio does not define the flower in some mystical way. It just describes the most practical composition. But what about the fuchsia with 4 petals? It doesn't follow the Fibonacci sequence. And the elusive 4-leaf clover may be rare, but it does exist. Why? Well, Fibonacci may have gotten a lot of press, but there are other variations that also converge on a golden ratio. The French mathematician Edouard Lucas came up with a similar sequence, except that it starts with 2 and 1. In fact, for every series formed by adding the 2 latest values to get the next, no matter what 2 positive values we start with, we'll always end up having terms whose ratio is phi. Eventually. Nature is indeed beautifully complex, but we can use similar approaches to understand many of its qualities. And it is not surprising that nature is this way, but it would be surprising if it were not.